Okay. Uh, so today, let me share the presentation. So one announcement, like tomorrow, as you know, that you are having your quiz, next quiz. So tomorrow the class is from 10 to 12, but we'll have the quiz at 11 o'clock. So initially we'll have some discussion. Initially we'll start the class, then the quiz will be at 11. Right. So 11 you need to join your. So for the quiz you need to be. You need to join this MS Teams and then log into Moodle and do your quiz. So MS Teams, you keep your uh, camera on 11 onwards. So it will be typically like last time, it will be for 15 minutes. Okay. Okay. Let me share the thing. Okay. So already you are working with SQL, which is primarily from the relational algebra representation. So we'll see today that relational algebra basic representations, which some of the things already you may be knowing from your set theoretic knowledge. And then we'll be also looking at, may not be today, tomorrow, that some other two forms of formal representation of the query. So why this formal relational query languages or representation is required? That will be, first of all, once we want to have a set of relations and want have some overall system in place that we want to have this type of queries to be answered. So we want to know that whether my relation satisfy those queries or not before basically putting into the system. Secondly, what we will see later on, that while optimizing a query based on especially this in terms of query optimization and query processing and optimization, we need to know that what are the different uh, variation of the execution trees, right? So if I have a query, so I have a execution plan. So there can be same query may have different type of execution plan resulting in the same output. Uh, so which plan will be more costly? Which plan will be more in terms of computational time, more beneficial, things like that, right? So some of the things which are, if there are say associative relations are there, then we can exchange the things like that, right? So those, in those cases, these are beneficial, which we'll be looking at somewhere end of this course, right? So when we talk about relational, so there first we'll discuss about relational algebra, and then we'll go to other two forms of formal representations. So when we once we talk about relational algebra, so this is a procedural language. So other two are what we'll see, that declarative. So this there are six basic operations you are already used to while writing your SQL queries, right? One is select, project, union, set theory, Cartesian product, and rename. So there are other operations which are either derived from this or have extension of those these operations. So the operations take one or more relations as inputs or more tables as input and produce another relation, right? So and select, project, rename operations are called unary operations because they operate on one relation, whereas the other three are binary operations, right? They work on two relations. So let us see one form of the that what are the representation for formal representation of these operations. So one is the select operation. So notionally we represent by this sigma p, that is a predicate over relation R. So there is a selection predicate, and it can be represented as that those tuple where tuple belongs to R and satisfy this P of T, where P is a formula in propositional calculus consisting of the terms connected by either this and or not type of things, right? So I can say that if department equal to physics and say student course equal to BTech, something like that, right? Or department equal to physics and say instructor designation equal to say associate professor or professor or something, then print select those instructor, right? So what it results in? It results in a set of tuples. Right. So from the instructor or from the R relation, based on this your predicate, it selects a set of tuples. Right. So there is a little bit confusion. Now you are basically used to it. So these are the set of operations which can be possible: equal to, not equal to, greater than equal to, less than equal to. So the term select in relational algebra has a somewhat different meaning that one what we used in SQL, right? The term select correspond what we refer to SQL as where, right? In the where clause. So that is there is a that nomenclature wise some confusion, right? So but in this case what we are doing, that from a relation R we are getting another output relation, say R dash, which is a uh, subset of this input relation. So other popular operation is the project. Which project? So here in this case we select a set of rows out of the available rows. So in case of project, what we select a set of column from the available column of this relation R. So A1, A2, A1, A2 are dot dot are the attribute names and R is the relation name. The result is defined as relation of k columns obtained by erasing the columns that are not listed. Like in this example. So from the again the instructor relation, what we are projecting the ID, name and salary. So it will be output as ID, name and salary in the this resultant relation. So duplicate rows are removed from the result since the relations are sets, right? Like suppose I want to only project the department name, right? So there may be a number of faculty members from the, or in this case number of instructor from the same department. So one department may repeated number of times, but as relations are in sets, so those are duplicate rows are removed, right? What we see in case of SQL also. So to eliminate department name attribute of instructor, in this case ID, name and salary. So instructor schema was originally having ID, name, salary and department name in the instructor relation, and when we project this ID, name, salary, so that those three are projected. So we result in a table or relation with these three attributes. So other unary union, another important operator is the union. That means defined as R union S, those two where T belongs to R or T belongs to S, right? So R union S to be valid, so R and S must be of the same arity or the same number of attributes, and also the attribute domains must be compatible, right? So that the domain of one should be compatible with the domain of the other one. So for example, to find out all courses taught in something fall 2009 semester or in spring 2010 semester, right? So or in both. So we want to find those courses which are either say spring, autumn, in our case autumn 2021, 22, or in the spring 2021, 22, or taught in both. Some of the courses like say DBMS is only on the spring, whereas some of the courses are only on the autumn. But there are some courses like ML or NLP. Those are as of now they are offered in both the semester. Right? So we can have this section, right? Semester semester equal to fall and year equal to 2009. So those select those course ID and union with the course IDs which are in the spring and 2010. It can be any thing, but only thing that one whilst union that arity should be the or the number of same number of attributes should be in your selection predicate. Another is the set difference operations where R minus S. That means those are in R but not in S, right? So that means defined as R minus S as those tuples which are in R but the tuple not in S. So set difference must be taken between the compatible relations, right? So R and S must have the same arity and attribute domain of the R and S must be compatible. So that is the condition or restriction. For example, to find out all courses taught in fall 2009 semester, but not in spring 2010 semester. Right? So, like course ID, this semester fall year 2009 and section minus course ID those spring and this section. Okay. So those courses which are there in the fall but not in the spring. So in this case, those in our case those courses like in our example, some of the courses, if in the other way around, DBMS will be there, but otherwise DBMS will not appear in this thing. In the spring. Okay. Set interaction operation. So R interaction intersection with S defined as R intersection is as tuple T, where T belongs to R and T also belongs to S. Right? These are already known to you. These are intuitive. Right? So assume R and S have the same arity. So that is the thing, that the condition attributes on R are compatible, and also we know that we can other way represent that R minus S set. Right? So those are the tuple which belongs to both R and S. So it will the output will be those tuples which are both present in relation R and relation S. Cartesian product is R cross S. We have seen earlier also. So defined that R cross S is those tuples T and Q. That means it will have both the relations where R belongs to T belongs to R and Q belongs to S. Right? So assume that the attributes R of R and S of S are disjoint. So this intersection, that is intersection is phi. That means if attribute R and S are not disjoint, then renaming must be used. Okay. So it is if in other sense, if there are m tuples in the relation R and n tuples in the relation S, then will result into m star n. So m multiplied by n number of tuples in the resulting relation in case of Cartesian product. So if there are same type of ID, a same type of attribute, like say teaching, say teacher ID or course ID matching, then I should have suppose R dot course ID and is dot course ID will be two different columns. Right. So it results into TQ number of columns. So the number of columns here, and there's the number of columns in say R plus number of columns in the S2 S relation. Okay. So there are other operations, right? Rename operations allows us to rename and thereafter refer to the resulting relational algebra expression. Allow us to refer to a relation by more than one name. So renaming x of e, right, returns the expression e under the name x. This is sometimes very helpful, especially when we want to do some sort of a self referencing type of things. In the sense, like I want to find out the say like in this book also you'll find, or rather in the slides it may be there, that the salary, the highest salary of the instructor. So if the instructor column is having the salary thing, so I need to join or make a Cartesian product with the instructor cross instructor. Right? So in that case, we rename it with this rename operator or rename operations. So rather, we can also rename the attribute. If a relational algebra expression E has arity n, then we can have this rename operator and x a1 a2 an with E. So results the result of the expression E under the name x now and with the attribute rename to a1 a2 an. So we can rename the things. So we'll see that in a number of cases this rename operator will be helpful in while especially while joining number of schemas or number of relations. So a basic expression of a relational algebra consists of either one of the following: a relation in the database or a constant relation, right? So E1, E2 are relational algebra expression. If E1, E2 are two relational algebra expression, the following relational are allowed, right? E1 union E2, E1 minus E2, E1 cross E2, that is a Cartesian product, renaming E1 to selection with a predicate P, and projection with a S is the list of containing some of the attributes of E1, that means projecting out the column. So in case of selection, we are selecting those tuples which satisfies that predicate. In case of projection, we project out those columns which are given in that list S, right? And then also we have a rename operations, which X is the new name from the result of E1. Okay. So these are formal representation or formal definitions. Other than this, we have some assignment operations. So provides a convenient way to express complex queries. Right. So like write a query as a sequential program consists of a series of assignments followed by expressions whose value is displayed as a result of the query. Okay. So write R join S, will come to that natural join as temp R cross S, right? Temp 2 as this selection RA1 is all those selection parameters A1 RA1 equal to SA1 and RA2 equal to SA2 and RAN equal to SAN on the temp 1, right? So what we say that we can assign to a temporary relation and then work on that temporary relation. So if your query, when the queries are complex, this may be helpful to express those things. So result to the right of this back arrow is assigned to the relation variable on the left of the vector, right? In this case, temp1 is assigned that, temp2 is assigned to this, value and this, and then finally the results what we do are union S project on that and on the temp2 relation. So may use variable in subsequent expressions. That is that what we did. What we see that extended. So these are the basic operations, and what we see that we can do some of these this with the expression, some of these formal operations, and then we have this assignment operations of taking an expression and assigning temporarily to a relations, right? So this helps us in basically simplifying the whole operation, right? So here what we did is a natural join. If you see in case of your Cartesian product, so the number of attributes will be pretty, number of tuples will be pretty large. So if there are m and n, so m cross n, right? So whereas number of cases what we require that this IDs or the what we look at it that wherever the column matches, they need to be equated, like what we did here, r dot a1 equal to s dot a1 and r dot a2 equal to s dot a2 and so on and so forth. So with these basic operations, we can have some of the extended relational algebra operations. One is the generalized projection, and there is a outer join and some of the aggregate functions, right? So again, some of the things already, or many of the things already you have already used in your for your SQL while writing the SQL queries, but we'll see that generic forms. So in case of generalized projection, so extend the projection operation by following arithmetic functions to be used in the projection list. Like so, we have this things like sigma f1, f2, f3. These are the functions. So as of now, what we have seen, this pi a1, a2, a3, an. So the field you want to project out. So here E1 E is a relational algebra expression. For each function f1, f2, fn, these are what we look at the arithmetic expression involve constant and attributes of the schema of R. Like here, in this case, what we can see that customer name and limit minus credit balance from the credit info. Right. Or we can something project as a, like if I have say salary, gross salary and the tax information of the instructor or the employee, we can have the net salary expressed as your gross minus tax and things like that. So this type of functional giving some arithmetic functions or arithmetic expression are possible in case of this type of projection, what we call as a generalized projection. So there are some of the aggregate function also we seen earlier, and you may be using it in your again SQL while working with SQL. So one is average. So average, which calculates the average value, minimum value, max, sum, count, right? So these are the 5 standard aggregate functions. So aggregate function, once we represent in relational algebra, so we represent as a representing this type of representing as a calligraphic representation of this G. And then we have on those things that function f1 working on a2, f1, a1, f2, a2, and so on and so forth. And we have a set of list of attributes on the things on which group can be done. Right. So I can say group by department. So you want to find out that total salary group by department, right? Or something courses grouped by department and so and so. So E is an relational algebra expression, and G1, G2 dot Gn up to Gn is a list of attribute on which group can be done. It can be empty, so I don't want to group anything, only on this thing like what we did at the things we can. So each Fi is an aggregate function, right? So that like it can be average, minimum, maximum, sum, and count, right? Ai is the attribute name on which this aggregate function will work on, right? So like especially in case of count, there is a thing called distinct count. So if I list say I want to count the number of courses offered by CS department in combining say union of autumn and spring 2021, then some of the courses which are offered in both the same, this course ID will repeat in the will be repeated, right? Like as I was telling that ML, NLP, and some of the courses which are offered in both the same. Right? So if I use the word distinct, then only one occurrence of that course will be displayed. Like here, relation account grouped by the branch name. So there are 3 branches. One is Perry Ridge, another is Brickton, another is Redwood. Right? So these are the account number, and these are some of the balances. Right? So branch name G sum, this aggregate function is sum on the balance and the account. So we have this Perry Ridge as 1300, Bricktown. Oh, sorry, I missed that. That it is grouped by on the branch name. So it is there. If the branch name is not there, it could have been added the whole thing, and the sum will be only the balance will be there. Right. So we have the branch name and the sum as the output attribute, and output attribute of the output resultant relation, and the branch name and that aggregate of that particular branch. Like in this case, Perry Ridge 1300, Brickton 1500, and Redwood 700 as the units at the balance. So result of an aggregate function does not have a name. Can use rename operation to give it a name. Right. So like here, for convenience, we permit renaming as a part of the aggregate operations. Like here, branch name. So in this case, the resultant do not have a name. So this relations we say that sum balance as the name of the resultant relation. Okay. Or sorry, the sum balance is the resultant of the in case of this yours. In case of the balance, I give that sum balance as the rename as that sum balance as a sum of within bracket balance as the sum balance. So the column becomes the sum balance. So in case of a natural join, what we see that it is basically take those which are common in the 2 attribute set. Like if you look at here, so what we see that sigma R1 A1 equal to R1 A2 and R1 A2 and R1 say in R1 A1 to S1 A1, R1 A2 to S2 S1 A2, and so forth, right? So matching those things. But in such cases, what is happening, if there is no match, those tuples are dropped, right? But I may want to keep those tuples, right? So it's an extension of the join operation that avoids loss of information. Right? Some of the things, if it is, so that it is not lost, I want to keep those things. Like if I have on the course, so those courses will be there which are maybe having offered in the both the semester. But I want to have all those courses along with that common courses, other courses also which are offered in autumn but not in spring. Right. So what happened in that case? It will result in those field as the null, right? So this outer join is an extension of the join operation to avoid that avoids loss of information. Though as such we do not encourage much to rather do not encourage keep null values in the database, because this creates lot of uncertainty while we do different type of operations. But nevertheless, in this case, our motivation is that to avoid loss of information. So there is a concept of outer join. So computes the join that and then adds tuples. Sorry, it should be from one relation that do not match the tuples in the other relation in the result of the join. Right. So it is like if we recollect that couple of slides back, so it is R1 dot A1 and R equal to S dot A1, say R dot A2 equal to S dot A2 and so on and so forth. Those things we do not match is the outer, those also taken into consideration. So uses null value. Null signifies that the value is unknown or does not exist. So on comparison involving null are false by definitions. Why we are taking roughly, we will see some cases there may be situations where nulls will like in case of a count, it will not count the things, right? So we'll precisely this comparison with null later on, so that how this null behaves. So like we have a relation loan, say loan number, branch name, amount, and relation borrower, John Smith, and this loan number as these other loan numbers, right? So there are two. So one is this inner join where loan and borrower, where all every matching will be there. There is a so where in this case what will happen? So if you see the loan number L170 and 230 are common in the two things. So this join or the inner join, what we see that loan number 170 and 230 are only showing up, right? Because it is an inner join. Whereas in case of when in case of outer join, so there are two outer join. One is the left outer join, another is the right outer join. So in case of left outer join, what is happening that we consider all the tuples of this loan account, right? Join with this thing, and whichever is not present, like L260 is not there, right? Whereas there is a L155. We are not considering for the haze, but what we are taking that 260 for that means it is the left outer join. So 260, whereas for the customer there is no customer with the loan 260 is updating as a keeping as a null. That means we are keeping from the loan relation all the tuples, right? So that later on if that those are used for some other analysis, but whereas this in the and for those tuples which are in the loan but not in that borrower, so that are those are kept as a null. Okay. Whereas there is a outer, so as it is left outer join, so there is a right outer join where this your customer names are there, right? That means this borrower the full set is there, but wherever the, so that's why we get L170, L230 and L155, but not the L260 as we seen in the left outer join. And here what we see, those are for those that haze is the customer name, loan number 155, where there is no loan amount or the branch name, there is no entry in the loan table, so that is kept as a null and both as null, right? So we have outer join as a left outer join and a right outer join, and then we have a full outer join. That means considering those tuples which are in loan, sorry, not in borrower, and also those tuples which are in borrower but not in loan. So there are those scenarios like we get some sort of this uh, union of these two left outer join and left right outer join. Okay. So though null values are not desirable in case of our database operations tables, but in this case, what our intention is that even with the null value that will handle later on in some appropriate way, but we don't want to lose any information, right? So this there may be scenarios where we want to do that different other operations like finding that total number of loans given or what are the different customers who had taken some loan from some branch and etc. So those type of things where we don't want to lose any information by through these join operations. Okay. Okay, this is about quickly about relational algebra representation, which is has a direct implication for your SQL this query is what you are writing. So this is a procedural. Rather, next to what we will be looking at, or next one is the tuple relational calculus. Rather, we will take up this one relational and domain relational calculus. These two will take up in tomorrow's class, which are declarative language. In this is what we see is a procedural language. Okay, so let us stop sharing this. Okay, so something. Okay, so if you have any query, we can take up. And again, just to tell you that tomorrow we'll have 10 o'clock. We'll meet. We'll have this race to things, and then will be the exam will start at 11. Right. So not exam, quiz will start at 11. So it will be typically around 15 minutes, and also you need to log into your uh, this MS Teams login so that keep your camera on and then work on the Moodle as you did in the previous quiz. Okay. Okay. So if you have any query, we'll take up. Otherwise, we are done for today. Let me stop the recording.